All right, we are officially into electricity now. So this PowerPoint, we're going to talk about principles of electricity. Also going to throw in that short slideshow about the power grid, even though that one's pretty basic, straightforward. So we'll try to get into it. So electricity is actually my favorite topic out of all these things. So what we're going to talk about here is the types of electricity, concepts and measurements, principles of grounding and bonding as safety measures, different terms, materials, and components associated with electricity, how currents work, how circuits work. We're not going to get into this so much, but understanding what different phases of power are as well. So it's important to note that there's two different types of electricity of current or static. What we're dealing with generally in construction is current, although static is sort of a byproduct of different mechanical equipment. But current, we're dealing with flow of electrons through conductors. So we're talking voltage, current, and resistance, as opposed to static, which is a buildup of electric charges where the measurements are more in joules and coulombs. Most often, like I said, this is what we deal with in construction is current electricity as opposed to static, but there is friction, there's motion, there's stuff taking place, so your building does have to account for that. It's just not, that's something more for electrical engineers to understand and deal with. Quick slide or a quick video here. I'll let you guys look through that with the slideshow, but just explaining how electricity works. Okay, different concepts and measurements. So again, we're talking current, right? We're talking resistance, we're talking potential difference, and we're talking load. So how they're measured, you're going to hear these terms a lot in the industry. So current is measured through amps, resistance is measured in ohms, potential difference is measured in voltage, and load or power is measured in watts or kilowatt hours primarily. So current is the flow of electric charge. It's measured in amps like we just mentioned. I like to also equate electricity into plumbing terms because it's a little bit easier to see how water flows. So this would be the equivalent in plumbing of what a flow rate is. So this is how much electricity is actually moving. Resistance is measuring how difficult it is for an electric current to pass through. So in plumbing terms, again, it'd be the equivalency of pipe size or having a reducer or having any kind of friction within there. Your resistor is a component that adds resistance to a circuit, right? We're reducing flow, we're adjusting signal levels, we're dividing voltages, we're doing all that kind of stuff. And then it's measured in ohms. So Ohm's law is measuring resistance. The general equation for it is current equals voltage times divided by resistance, sorry. So I equals V over R. Some of the things so the wire that we use by itself is resistance, right? So if we're talking about pipe size for plumbing, it's also the wire gauge. So if we're talking 14 versus 12 versus 10, that it's in itself is resistance and not allowing flow through the circuit and the material. The other one is a voltage that we have to deal with. V primarily. E is another one that we use, but not necessarily for construction. Difference in electric potential energy between 2 points per electric charge. So this one is something that people have to understand, or it's a little bit harder for some people to understand. It's really dealing with pressure differential. So again, the measurement V equals IR, equivalent in plumbing terms to like water pressure. If there's no pressure, there's no movement. So if we have a balancing of voltage and everything's balanced across and there's zero voltage, there can be no flow. So we're moving from a high pressure state to a low pressure, just like we would in plumbing. And the term voltage drop means how much voltage we lose over throughout the circuit or throughout a part of a circuit. So just like in plumbing or anything else, the further you get away from the source, the more pressure you lose. So the same thing happens in electricity. The further we are away from the source, or the more resistance we have throughout the circuit, the more voltage is dropped. So when we're talking transmission and going to like the power grid and everything, the further we have to transmit power across, the more voltage we're going to be losing throughout. And then the last major component is load, and this is the component that is consuming the active electric power. So this is our lights, our outlets, appliances, equipment, etc. We measure power in watts. Oh, animations are off a little bit. The unit of power being used by the load, it's P equals V times I, so P equals VI. Watts equals volts times amps. So sometimes you'll see also in plans, you'll see volt amps. It means the same thing. And it measures that rate of energy transfer. More watts equals more energy consumed per second. So that's why we're often seeing our measurements in kilowatt hours, because we measure that consumption over time. Okay, a couple safety terms. Electrical grounding. And what grounding means is it's a method of providing a live part of an electric circuit the most effective way to return to ground or the earth, right? So electricity is constantly flowing. We need a place for it to go. So grounding is an important piece of safety. If we do not have grounding in place and you touch that current, you become the ground, and that's how we get electrocuted. So any kind of overcurrent, right? So if we open up space for that electric circuit as it's, if the wire's hot and we touch it, we've now just created basically a floodgate. Like imagine a dam breaking. Now all of a sudden we have a lot of space for that electricity to go, and it's going to go all throughout you. So we want to prevent that overcurrent from happening. So we want to be able to provide a direct path to ground. Since Earth is relatively large, it absorbs and it disperses that electricity throughout and basically kills the ability for you to be electrocuted. Talked about that. So the other important concept along with grounding is bonding. You're generally going to have to do both on construction projects. So what bonding means, though, is this is intentionally connecting all of the exposed metallic items within a building that are not regularly designed to carry electrical load. So anything that's not supposed to carry electricity, we connect them together. Purpose being is once we have all those items bonded together, it balances out the potential difference. So that's talking voltage. And if our balancing out the pressure throughout, there's nowhere for that pressure to go from high to low pressure. So the voltage or the current can't flow. So pretty important safety measure. There's always been, since I've been in the industry, there's like some sort of a debate about are we grounding things, are we bonding things? I think we're kind of doing both, right? We kind of interchange them because what we're technically doing in all of our buildings is we're bonding everything together, but then we're also taking it to ground. I've heard the term earthing used before as well. So this is where we're taking all of the dead bonded items within a building and providing a grounded path or paths to the earth. So it's kind of what we're doing in general is earthing. But you'll hear different terms a little bit interchangeable throughout, but this is what all those three things mean. Okay, moving into currents here, we have two types of currents. We have alternating currents, we have direct currents, and apparently dad jokes are coming out because we have to see that you've been thunderstruck. Okay, alternating current. This is when we have electric current that is constantly reversing direction. We use AC current to distribute power throughout the transmission, throughout the grid, throughout our buildings, pretty much everywhere. It's produced by a generator using two main components. We have a stator and a rotor, stationary and a rotating part. I'm not going to go into too much depth on how the generators work, but here's a sort of portable one. Here's a smaller one for like a light commercial or residential home. It's probably a little big for a residential home, but different examples of them. We would use generators in our facilities for backup power, not really for primary power, because we can typically pull those right off the grid. We use our smaller generators, obviously, for temporary power during construction. Have a short video here as well for you to look through to just see how the generator actually works and creates that electrical power. But it's important to look through that too, because we use the sine waves that are created as a representation of how much power is being distributed within that current. So this sine wave here represents one cycle of a generator's oscillation. So as that generator is oscillating around, doing one circle, we're going, this is a quarter turn, a half turn, a quarter turn, and a half turn. So we're getting max power, dropping down to no power, to max power, to no power, to max power, to no power, all the way throughout. So that's a sine wave that we're creating as that rotating part of the generator is passing by the stationary part of the generator to create that electromagnetic reaction. So, and then the frequency of how often the sine wave or how often we rotate is measured in hertz, right? So it's a cycles per second calculation. The higher the hertz, the faster the rotation of the generator. Direct current, on the other hand, is an electric current that's flowing in only one direction. And we use this for things like charging batteries, a lot of times, obviously, automotive and aviation applications, anything that we can't connect into the grid. So battery operation, when we're talking power generation, solar panels produce DC power. In order for us to transmit that power, we have to invert it to AC power first before we can actually transmit anything. So end use things, everything that we plug in, the computers you're looking at right now, the phones, all that stuff require DC power. So we also have to convert that AC power into DC when we plug items in for that consumption. Okay, for AC versus DC. So AC is very efficient at distributing power over long distances. Very low amount of voltage drop. All of our homes and outlets use that AC power. Inverter converts DC to AC for any applications that require that. DC is a lot simpler form of energy generation. Like all these, like I've just mentioned, all the different items that we use as our end use products require DC that we plug into the wall. Okay, I like to use a water analogy as well to show how alternating current works. So if this is our generator, right, and it's spinning around in a circle, we're pushing the water back and forth, and it's constantly having somewhere for that current to flow. In a DC situation, we're basically just unplugging a hole and all the water is rushing out, and whatever happens over here is being used and consumed. So so the efficiency is pretty much gone there, except for if we're just using that end use source. I'm not going to go through series and parallel too much, but this is kind of going back to the basics here. But a series is when we have a current that passes through a component on one loop. The voltage across that circuit is the sum of all voltages across each component. In a parallel circuit, though, we have two or more pathways for electricity to flow through that circuit along that same loop. And then all the components across the circuit have the same potential difference throughout. So quick little description here, we have battery power, and we have a series connection. So at any point, right, so the old Christmas light bulb issue, one light bulb goes out, the whole strain is out, right, as opposed to a parallel connection where we have one light bulb that goes out and the rest can maintain. So it's also important to note that in a series circuit, as the overall amount of resistors, so in the last case, light bulbs are added, the overall current decreases. Right? So if you look backwards here, so the more resistors we add, the current that we have going across all of them is decreasing, as opposed to parallel, where as the amount of resistors are added in new parallel circuits, the amount of resistance decreases, right? Because we're providing new pathways for everything to go. So I like to use the old toll booth analogy for this one too. So if we have a single resistor on a toll booth, everything gets funneled to that one resistor, right? And we're utilizing all that energy at that point. If we put multiple resistors in series, we're slowing things down even more, right? But if we're adding resistors across parallel circuits, then we're providing additional pathways. Pretty good analogy, not exactly how it works, but pretty close. And then the last thing I want to talk about here is phases of power. So you're going to hear about single phase, you'll hear about dual or split phase, and you'll hear about three phase. So single phase is the most commonly used. We use it in homes, small commercial applications, all that kind of stuff. We produce 120 volt circuits for all this, and this is typically what we use for almost everything in our homes except for more dedicated things like refrigerators, stoves, water heaters, furnaces. Those kind of things are typically on your dedicated circuit. A washer or a dryer probably would be on its own. In this situation, we would have to have one hot wire, one power wire, a neutral, and that power is going to flow between the two throughout the load, right, whatever that might be. So the light bulb, right? So as we turn that light bulb on, then that power is being delivered through the hot wire and flowing across both. We also have a ground wire for safety. So anytime you'd see something like 14-2 wire, that would be like a standard for your lighting. Then that would be that 2 indicates that we have a hot wire and a neutral wire, and then a third wire would be a grounding, right? So if we have a 3 wire, 14-3, that means we have a hot, a neutral, and a secondary hot, which would be a red, and then we would have also a ground. So there's actually 4 wires in there. Get into that a little bit more in the wiring connections PowerPoint. Dual or split phase is basically just two single phases put together. So a lot of household appliances would require 240-volt power for different circuits, like appliances equipment. So at that point, we're just basically doubling this. We have two going on simultaneously. And then we have three-phase power. There's a diagram or a little video here too that you can click on to see how three-phase power works. So this is used in a lot larger commercial applications, industrial applications, anything like that. A lot higher power density and capacity, and a much more efficient way to produce or to use that power with a lot less voltage drop during a cycle. This is a good video to show how that works, but I do want to show how the sine waves work and how you'd see them on a set of plans. This will be the last thing we should talk about in this PowerPoint. So on a set of plans, you'll see a line, right? This is your hot line. This is your neutral line. We're not going to show the ground on there because that's just for safety purposes. And we have a resistor. That load is 120 volts. I shouldn't say the load, but the voltage is 120 volts across both as we're using whatever that load might be. The single phase power and the sine wave would show something like this. So we have 0 voltage up to whatever that max voltage would be, and then down every time. So we're always going back to 0. So if you're using single phase power, what this means is if you actually we're able to take video of a light bulb at an extremely slow pace, you would see that that light bulb is flickering because it's constantly going at a really fast pace to max power to no power to max power to no power. Okay. In a dual system, we're basically doing the same exact thing, we're just duplicating it. So we have a hot line, and a neutral. So we have 120 volts across both of them and 240 across the two hot wires. So the waveform is opposite then. We have max power on both down to 0, right? And they're just running on opposite, but they're creating double the amount of power needed. In a three-phase, though, we have 3 hot lines coming in with a neutral, right, across all of them. So we would be adding a lot more power across the board, but these are also staggered, right? So now our voltage drop is not going to 0 at any point. It's going from max down to about a half, to max to half, to max to half. So this is how three-phase power works. It can distribute power a lot more efficient and with a lot greater capacity. The more phases you add, the more capacity you add, but it's kind of determined that 3 is kind of a really good number for it, because as we start getting into, like, say 6 or 9 phase power, the infrastructure requirement is so high that you're not really getting that return on efficiency that you would hope for. So 3 is sort of the number that's been settled on. Okay, and I do want to go through really quickly just the power grid. I'll let you guys kind of go through this mostly on your own, but I'll skip over a lot of this stuff so you can just see this, just showing how the transmission works from the process. Okay, here, keep going. But I do want to show the building distribution at the very end. Couple pictures of step down. Okay, so if we have a small building, after we get through the whole transmission process, we would have typically a transformer that's owned by the utility company outside of your facility. We'd have a meter that's owned by the utility company outside of your facility, and then after that meter is when we start coordinating and connecting in, pulling the panel or hooking up the panel and running our branch circuits throughout the facility. Pretty basic, pretty straightforward. Once we get into bigger, larger facilities, we have to deal with our own transformers, our own switchgear, and a lot of our own methods of transmitting power throughout the building. So after the meter, we would have our own transformer that steps down power to whatever we need it, or divides power to wherever we need it. That goes in the switchgear. This switchgear, I'll talk about that more in equipment, but that basically controls your whole building as far as how much power is being distributed. Then we distribute that across bus bars or feeder bars all throughout your facility into their own different branch panels, right? And those branch panels might have their own transformers on them as well, just to step down power even further. So we're constantly creating a lot of power at the big energy generation plants, whatever that might be. We step up that power at that first step on transmission lines, and then from that point on, we're transmitting power, stepping it down at the next transformer, branching it out, stepping it down, branching it out, and then getting into our buildings, whatever their final needs are. And the same thing happens throughout the facilities too, as you can see in the last slide. This is the last one, just showing different forms of energy generation. We basically have it broken down to three categories. We have combustion, we have motive, and we have solar. I'm not going to go into this too much because we're going to do a small group project and presentation on this in Module 4, but within combustion, we have fossil fuels, which commonly are coal, natural gas, and oil. And then we also have nuclear, which is primarily uranium. In the motive section, we have hydro and wind. This is just using some sort of resource to turn a turbine of sorts. So these two actually operate very similarly, just using water versus air. And then solar, we actually have two different types. Photovoltaic is what we use for electrical energy generation, and thermal can be used for energy generation, but really not efficient at all. And we use it more for heating water for different uses, and you're mostly only in like desert areas where you get a lot of sunlight and not a lot of water. But that is all I have for this one. So yeah, if you have any questions, let me know.